Thank you, Dr. Martas, and thank you, everyone. The topic of the presentation is structural health monitoring, and I'll share a couple of case studies, what we have implemented in Kuwait. You know, SHM is a relatively new topic, especially in civil engineering. I started my career in aerospace engineering. I was a scientist in Ministry of Defense, where I used to work on the fighter jet. Those days, we used to do monitoring of aircraft structures, and actually I was responsible for monitoring. And I remember that was in 2006. We had 4 sensors at the most very critical component of the fighter jet, where the fuselage is connecting to the wing. We call a very important structural frame member. And I used to ask the pilot to do certain test flight and certain specific maneuvers. You must have seen in air shows, the fighter jet is rolling and a free fall. So we used to do very specific maneuver. And after the flight for 20-25 minutes, I get the data. And with these 4 sensors, the measurement rate used to be 3 data points in 1 minute. And after 20 minutes, you can imagine 3 into 20, 60 data points. So those days, the sensors used to be extremely costly. And also the data analytics, we were using only physics-based methods to identify the damages or any change or performance, structural performance. And from there, Ashur, who is working with me now, what is the measurement rate of one sensor? We get it from Alhambra? 200. Initially we started with 500. If you look at turbine blades, it is 10,000 data points per second. And we put hundreds of sensors. That's the way it has grown. Especially for the past 5 years, there has been a significant advance, and it has become affordable even in civil engineering. And I'll share a couple of things what we have here. So, in a nutshell, structural health monitoring is nothing but we keep sensors at critical components of the structure, whether it could be a building, a bridge, wind turbine, aircraft, anything. And what are where to keep the sensors? That's a different story, but at critical component. And what type of sensors we keep it? That's again a different story. And these data from different types of sensors are analyzed, and we interpret the performance of the structure, if there is any damages or any specific information we want. It depends on the type of information we want. For example, it's just like when we go to a doctor, right? He check our pulse rate, blood pressure. In case if it is necessary, he will ask for more and more details, isn't it? That's exactly what happens in structural health monitoring as well. To start with, how do we do? If somebody asks me, when we say in structural health monitoring, what does that mean? What type of data we collect? Those are the things I am going to highlight here. This is a very important success story. This really happened in Netherlands. There was an issue of structural issue for a building, and they installed the sensor. They installed the sensor in one of the very critical column. This is it was a strain sensor. Within few days, a couple of days, they noticed a very high strain deformation of the column. The 4th day, they were asked to vacate. Within 24 hours, the building got collapsed. That's the value of, they evacuated because of the warning, and after evacuation, within 24 hours, the building collapsed. So that is the value of SHM. And in this case, they knew where exactly to be placed. So at KISAR, we monitor a couple of important, we have also added additional infrastructure which I have not added here. We are monitoring Alhambra Tower. I'll share some of those details, what we are doing there. We have also monitored a highway bridge. that is in the Fahil Highway. You come from Salmiya to Kuwait City. This is over the Cairo Street. So that bridge we monitored during the construction of the I think they were making a trough and building a couple of flyovers. But this particularly, the bridge in Fahil Highway we monitored during the construction, and Masjid al-Kabir. If I have time, I'll share a couple of things what we are doing at Masjid al-Kabir. Now, the question is, why do we need an SHM? Is it really required? I think this is the question first. Everyone asks. If you ask a client, if I ask Aziz if he has a new project, if I propose, he will pose me the same question. Jafar, why should I do this? What the extra benefit I get? Right? Let's take a simple scenario. Suppose we all are sitting here. Unfortunately, an earthquake hits and the building vibrates. And what should we do? Right? The question comes as, should we evacuate or can we stay? The earthquake happens for a short period, right? Vibrates. Sometimes nothing happens to the building. What should we do after the vibration? Think about a building like Al-Hamra in the middle of the night. I remember a story I think that was in 2017, if I am not wrong. There was an earthquake in Iran that's around 700 kilometers away from Kuwait. And I think it caused vibration in many of the buildings in Kuwait. And I remember people were standing outside, all the residents standing outside their apartment in the night with children. So nobody knows what to do. Can we go back? So think about the evacuation in the middle of the night. Evacuating an entire apartment. And in reality, if it is not required, you can see how much struggle the tenant would have taken. The second scenario is, we were supposed to evacuate and we are not evacuating. That's even more dangerous, isn't it? So this is the uncertainty. This is a part which clears. If we have a sensor, we will come to know exactly how much the safety factor we have, how much the building has been moved, and we will be able to take the decision based on the exact measurement. There are various other reasons which I can give hundreds of reasons. One of the major reasons, I would always say that if you don't put any sensor now, we cannot collect that. For example, I give an example. I would like to see how I was when I was a baby. You know, how I played. Unfortunately, I don't know how I played, how I looked like, simply because I did not have any of my videos and photographs when I was young. Now, can I get it back? No. Why? Too late. It's too late. Simply, I did not take it. Why did I not take it at that time?
Your parents did not take it.
Yes, she's complaining my parents. I will also blame my parents. They didn't take. Do you know why they took that decision? Pardon?
Maybe technology is not there.
Technology, is it correct? Technology was there. There are lots of cameras. Yeah. What could be the reason? Awareness.
Knowledge was not there.
No businessman here. Cost. Exactly. They thought that it was very costly to get a camera. But when I look at the value of those data now, I would have paid 10 times what it was costing now. So the past data is gone. I always tell them. Because these sensors are very cheap. So it's extremely, even if you don't analyze, it's extremely important to collect the data for the future purpose. But the most important, the current value is this. And I can even tell you what happened in Al-Hamra immediately after the earthquake. How much they were valuing about the data what we gave. At that time, we did not have much sensor. We had only one GPS. I'll tell you that story later. So what are the additional benefits? One benefit I already told, it can give early warning system. Early warning system in a sense, see I cannot run the same way, as if I am 17 years old, right? I'm getting old. So we all have a natural deterioration. This is very difficult to track. This is one. The other thing is if any extreme event happens, such as an earthquake or a heavy wind, what is the damage it has caused to the building? This quantification can actually affect the life of the structure. So if we can actually get an early warning system, how much is the remaining life? What is the status of the structural conditions of the building? So one of the major advantages, it can provide early warning system, and it can give real-time information immediately after an earthquake. One of the extremely important thing which I have experienced during my work is, for example, the work at Al Hamra, the work in the bridge, I will share those. This is for the local design code. That has a very long-term impact for the country. See, many information, for example, if you look at the temperature, if you look at any of the codes, I don't know whether we consider the cyclic temperature effect in the design. Kuwait has a totally different ambient loading conditions compared to the rest of the rest of the countries, isn't it? We experience more than 55 degrees Celsius in summer, and when it goes to the wind, it touches 0 degree. Not only that, if you look at the temperature data in summer, the diurnal variation can be more than 20 degree in many cases, diurnal daily variation. So how does this affect this building? Do you think a building move due to temperature? No, he doesn't agree. I'll show you some data. So there are some local information. If you want, you have to have a long-term data collection that will in the future will lead to the development of local building code. I'll give you another simple example. Have you, one of the major issue of the roads in Kuwait, we feel it is getting deteriorated faster, right? One of the obvious reason, we all say that the temperature. Do you know what could be the other reason? You know, pardon?
Substrate preparation.
Substrate preparation, yes. What else?
Temperature variations.
Yeah, temperature variation, that's correct. So there could be various. One of the local information which we can think of is what is the type of vehicles, what is the number of cycles of vehicles it is getting loaded in the road. There is no mechanism here to take the weight of the vehicle, isn't it? The life of any structure depends on the number of the cyclic loading, isn't it? So this information, so if you want to design a road here, you have to have those data, right? So the local data is very important. So structural health monitoring and the data collection actually significantly contribute in the long run for the development of local code to derive actual coefficient, more relevant coefficient. And this is very relevant to us. This is a new technology, and it is a data-driven technology. And as all of you know that whenever we talk, wherever we hear these days, we always talk about AI or data-driven technology. And that is actually 5 years ago, many of the data-driven technology was just a buzzword. Now I can tell you from our own experience, some of the data-driven methods are so accurate, much more than physics-based method. So being this is SHM is a new technology to civil engineering, there is a lot of opportunity for research and innovation. Early warning system we have talked about. Now, this is a very interesting question I posed first time. When you talk about SHM, what should I measure first? Tell me, my building there is no issue with my building, I'm very healthy. What should I do? What should I measure, right? In general, if you look at, you can measure anything. But in general, if you talk about structural health monitoring, and civil engineering, we do structural health monitoring. Sometimes it is not continuous. We do field inspection, visual inspection. We do take some time core test. There are various testing we do, non-destructive testing. But in general, when you say structural health monitoring in this modern term, one of the term what we is based on the approach we call global SHM. The other one is local. What does this mean by global? If you want to know the overall structural condition, this is what we call, for example, if you have some issue on a crack on a beam, that may not pose the complete structural threat on your entire structure, right? So, in general, one of the things what we first should do is a global structural health monitoring. That is also, it comes under the bottom one. If you want to know the global structure, the global condition of the structure, the easiest way is to measure a vibration. If you want to know the global condition of the structure, the best way is to measure the vibration data. What does it give you? I will give you why this gives you an information about the global structural condition, the math behind it in the later part. So what does this also mean? We cannot get a small crack in a beam. We cannot get the details of the damage. Okay? The other thing is, we say the local. If you know that some of the structural component have got some issue, so we want to monitor that particular location, then we have to either measure the strain. In that case, if you measure a particular location based on strain or displacement, this will give information only about at that point. It cannot at that location or at that region, around that region. It cannot give you the overall condition of the structure. So when you say structural health monitoring, always we start with the global based SHM. Based on some data, we go back and monitor certain critical component. Or if I already have information about the structure, we can always monitor the critical component locally. And in general, it's a combination of all. But if you do not know what to do, the easiest way is to measure the vibration and assess the global state of the structure. And when we talk about SHM, generally we say continuous monitoring. That means the sensor will be lying in the structure full time or for a long period continuously. It will be installed permanently, at least for continuously for 6 months, 1 year. So this is just a classification. The periodic monitoring, we all know that. We go for visual inspection, so on and so forth. Another very important component is sensor. What type of sensor we should use? There are various types of sensor available. Even if you go for vibration, you can measure lot of parameters. In vibration, you can measure velocity, you can measure acceleration. What sensor I should choose? So in general, these days, we have very sensitive, very accurate vibration measuring sensor. And if you want to measure the strain, there are various, it is not the laboratory scale strain sensor. We have something called optical strain. These days it's very popular now. This can be run continuously. You can measure 1 meter or 2 meter length and this will last long. Usually the laboratory scale strain sensor, this is what they do it embed in the reinforcement, but they may not last long. So in structural health monitoring, there are 3 components. The first component is the hardware. The second component is the data analytics. And another component which people usually don't talk about is the computational model. So in general, computational model is very critical in the beginning of the monitoring, where to put the sensor, how many sensors you need, what type of sensors you need to choose. So the finite element model, in general, for us structural engineers, this is very crucial. And also, during the monitoring, these days, digital twin is a very common term you might have heard. Digital twin, actually, the first people digital twin started is from aerospace industry. So it's nothing but you have a very accurate computational model. Your finite element model during the design stage, it could go various changes. Not only that, you know that the civil engineering, right? If you test core samples from one place, you get a different strength. If you take from other side, you get a different material property. So once you have the finite element model, you can always tune it based on the measurement. So the first, and one important component is the computational model. The second part is sensor. What type of sensor do we choose it, and how many numbers? And these days, why SHM has become very popular? This component, the price has come down significantly here. And now everything is a sensor. These days we are doing in my lab, we are just recording the video of a building. I don't need to put any accelerometer. I can extract the acceleration, and which we were able to match with the accelerometer, even a video. Everything is a sensor these days. Now, the most important part is the data analytics. And I will be showing the physics-based indicator for damage identification. But these days, the data analytics has been improved significantly, and many mathematical parameters which has no connection with the physics can give very good information about the conditions of the structure. We have recently published a couple of very good papers on purely machine learning based parameter. These are some of the different types of sensors. These are actually what we have used. The top one is an accelerometer, and by the way, we use even a GPS to monitor the movement of the building. I'll show you the results what we got it from Alhambra. And we also use something called an inclinometer. An inclinometer actually measures the inclination. What does it give us? If you know the inclination, we can actually calculate the displacement. So this accelerometer, it gives acceleration. We can also have, sometimes you might hear seismometer. It measures velocity. Though the difference is, for example, a short building like this, a short building, the ground floor, during the ambient condition, it's sometimes very difficult to measure the vibration. Mostly you will get noise. There is no data. In such cases, seismometers are quite good. Where the vibration is at very low amplitude, seismometers are quite good. Then GPS, what do we use it for? It's actually really a multi-purpose sensor we came to know. So it started as a research project, and interestingly, it came out in such a way that this is a really multi-purpose sensor. By the way, accelerometers, as I said, this is quite suitable for a global, to understand the global conditions of the structure, but it's very difficult to extract anything about the seasonal change. For example, due to the temperature. With the accelerometer, you cannot. But on the other hand, if you have a GPS, that can be, you can measure how the building is performing over a long period. For example, the seasonal change. These are the data logger. I think I will skip. This is the optical stand I'm talking about. By the way, this we can get it for a continuous long. These days, for example, underground structures, tunnels, they run the complete cable, and you can choose a point and what type of data you wanted. That's a continuous fiber optics. But this fiber optics is, it measures over a 1 meter or 2 meter. This is really an industrial scale, and it lasts quite long. We have used this for the bridge. This is, now, to know the vibration-based, I will talk mostly about the vibration-based structural health monitoring. Some of the very basic concept of structural vibration is crucial. You know, we all are structural engineers, and these are all for you maybe looking an undergraduate course. If you have a structure, it is associated with elastic, right? Elastic component. We have associated, usually we see the spring mass system is what, when you open any structural dynamics books, what does this represent? This represents a building, this represents the dynamics of a car. What are the elements of corresponding to the building? K, there is something called a K we call stiffness. that is the elastic components of any structure. Could be a building, right? Now the mass, that is related to inertia, and we call the damping component, which brings down the response, die down the response to zero after some time, the damping component. So if you write the equilibrium equation of this, you can see there are three components. That the inertia component. Inertia component, nothing but just Newton's law. Mass is directly proportional to the acceleration. That is the first component, mx doubled. It's a d square x by dt square. The second part is the damping part. That's again a nonlinear term. The third part is stiffness multiplied by the displacement. And you see that all these components are forces. Mass into acceleration, that is the first component, velocity into damping, and stiffness into displacement, and the external forcing. In dynamics, you have to understand everything is a function of time. Your displacement, whether it is strain, your element force components, everything will be a function of everything will be a function of time, right? Unlike static. Now, the equation what I have shown here is nothing is called a forced vibration. But interestingly, to solve this equation, you can recall, we solve this equation in two ways. We call a complementary function. I know I'm going a bit technical, but just I want to highlight, and particular integral. So the first part, the complementary function, we put f of t is equal to 0. So if you look at the static case, you have only kx, right? Those who are the structural engineers here, design engineers, kx is equal to f of t. If you put the right hand side 0, we don't have any solution, right? Isn't it? There is no force, there is no displacement. But that's not the case in dynamics. If you have a right hand side 0, you can get a solution. This is called an eigenvalue problem. And what does this eigenvalue means? If you solve the right hand side, put 0, you can extract the natural frequencies of the structure. You must have seen when you run ETAP, you run model analysis. In some software they call free vibration analysis. In some software they eigenvalue analysis, right? That's actually when you put f of t on the right hand side, that's the complementary function. So whatever you extract is the natural frequencies of the structure. Why is it important? Why am I talking about all this? So the natural frequency of any structure of a spring mass system, which is represented like this, is given by square root of k over m. What does that mean? K is the stiffness, m is the mass. So to change the natural frequency, only two parameters need to be changed, right? Either k or m. So a damage happens to a structure. What component of this will change? Stiffness. That is the whole idea of vibration-based monitoring. We assume that there is no changes in the mass. If any changes, if I can track this parameter, if I can measure the natural frequency of a structure, I can actually track the structural condition of, because if this has to change, K has to be changed. That is the fundamental idea of vibration-based structural health monitoring. And it's very interesting, I can tell you, the natural frequency of any structure is like a DNA. It cannot change unless otherwise K or M changes. It's very unlikely that M changes, right? So that's why I had to explain. I think I will skip this again, how you, in general, if it is not a simple equation like this. For a this is I have shown, I think you all are familiar with the degrees of freedom. The system what I have shown is a single degree of freedom system. That is why you are getting a simple algebraic equation. But in a multi-degree of freedom system, all are matrices. K is a matrix. So if you have a 10 degree of freedom system, you will have 10 eigenvalues or 10 frequencies. That is why in your ETAP analysis, it will ask you how many eigenvalues you want to extract, right? So if you put 200, and if you have a finite element model of 100 degrees of freedom, it cannot give you 200 eigen. Have you ever tried? Anybody runs ETAP here? You run? Yes. Yeah, I think all of you run industrial scale. So usually the number of degrees of freedoms are very high. So anyway, it depends on the number of degrees of freedom. I will skip this portion. I'll show you a very interesting phenomenon. So if you oscillate a pendulum, right? You know all the pendulum. So if you give an initial displacement and leave it, what happens after some time? It stops. Excellent. Do you know that if I assume there is no damping in the system, I get a solution like this is x of t. X of t is nothing but how much it moves over time. So it is a function of sine and cosine. If you plot sine, what does a sine wave look like? Will it ever stop? No, right? It will never stop. So if I want to predict the vibration of a pendulum, this, by the way, this is exactly the same as vibration of a building under earthquake, right? So an earthquake happens, during the earthquake there is a force. After the earthquake stops, it's a free vibration. Okay, so it gives an initial condition. So if I don't assume damping, if I neglect damping, my model will tell you that it will never stop. But that is not the case. The moment I incorporate damping, you will see that the system dies down. That comes from the e raised to minus c minus e raised to sigma t term, where sigma t is a negative, it is a damping coefficient, it brings down. Anyway, in our analysis, in our ETAB or any structural analysis software, the free vibration doesn't change, your natural frequency doesn't change whether you include damping or not. That is why I brought it here. But when you do if you want to see the response, you will see a lot of difference. But if you want to calculate only the eigenvalues or the frequencies, the undamped or the damped vibration, you will get almost the same results. That's because I hope I have put the equation here. Yes, omega d is equal to omega n into 1 minus zeta square. Zeta is a very small value. Again, I just want to reiterate, the very fundamental concept of SHM is it will change the frequency if there is any damages in the structure. It's not only on the frequency. I will bring another term. This is known as a mode shape. Okay, the eigenvector. The mode shape also changes. So we also look into this. And you will also see that the damping also changes. But in general, the first indicator comes from the natural frequency, the first term. This is, I have just rewrote. If you have the damaged stiffness, you can actually estimate what is the, you can actually quantify the damage. So you can see that what are the major parameters in the stiffness, right? If you have a beam or a column, right? You have majorly three terms. One is your material term. You have the inertia term. It can be I or A, any related term. And you have the length, right? Geometry and the material. Usually the material degradation is not very high over a short period. Mostly it will happen. It will be reflected due to the inertia and other geometrical parameter. So in general, we can calculate an effective an equivalent reduction in the stiffness. Okay. And another very interesting thing. Usually we have a multi-degree of freedom system, but we can always reduce your model into a reduced order model. Suppose you have a 100 degree of freedom model, you can always calculate, you can always make your finite element model a reduced order model without changing these model parameters. That's actually for the computational purpose. So if you look at your car vibration, how do you think the costly car has a very comfortable drive even over a hump? They design their vibration characteristics very, very accurately. But interestingly, it's just a single degree of freedom, a 2 degree of freedom system. I think I have to rush. Maybe I will skip. By the way, these vibration sensors are nothing but it has a spring mass system inside. So let me very quickly go. We have done Alhamra, one of the first projects we implemented in Kuwait on SHM is the Alhamra Tower. And this is done as a research project between KFS, Kisar and Alhamra. You know, Alhamra Tower is one of the tallest, this is the tallest building in the country. And this is, they say that the tallest sculptured tower. I don't know what is the definition of it. So a sculptured tower in the world. And one thing I can tell you, if you want to design a structure like this, many of our design codes will not help, isn't it? Especially the wind load. Can you calculate the wind load based on your code? It is impossible. If you go to Alhamra Tower in some of the floors on the top floors, I used to go to put the sensor. You can see, it is like, you must have heard stress concentration, right? Near the hole, the stress increases significantly. If you do, so this exactly happens even the velocity. A stream of wind stream enters the building, and if it has a cavity like this, the velocity increases significantly. So the wind speed, what you calculate from a code, will go totally wrong. That's where they are. You have to either go with a wind tunnel or you have to go with a complete CFD. Usually, even the wind tunnel in aircraft, in aerospace industry, we actually even match with the CFD. So anyway, this is a very, very architecturally, very Aziz will like it because it looks very nice. But the problem is it gives a lot of struggle to Mansoor, right? How do you design? So architecturally it is quite appealing, but it will bring a lot of complexity to structural engineers. So, and you can see that if you do look at the vibration characteristics, you can see the torsional more. Anyway, I think I will, it's a very interesting building, you know. It has a square, it is actually square in plan. But what happens, one quadrant is open, and once you go higher up, this quadrant, it gets rotated. So this is at the bottom, this is southwest, and if it goes on the top, it changes into northeast. So this actually brings a lot of torsion, isn't it? And if you do, what does that mean? If you apply, so if you, in a normal structure, if you apply a vertical load, what happens? Do you get a horizontal displacement? You know what happens to this structure? Simply because of the torsion, it rotates. So if you apply a simple vertical load, you also get a horizontal movement. And you know that unless otherwise a circular cross-section, it will cause warping as well, isn't it? So anyway, so this is highly torsional, sensitive. And the structure is one of, I think this is one of the prestigious building, and even it won ACI award. That's because of the challenges it brings and the architectural shape. And this is one of the outstanding building. So we have a very dense instrumentation here. What type of instrumentation? When we started, we also did not know, by the way. Let me tell you, we also did not know in the beginning. Of course, we know that we have to put, that was certain. So we started with accelerometer, and we also started GPS just as a research project. And it came out that GPS is an outstanding sensor, and it has a multi-purpose, it can be used for a multi-purpose. So we have used here 3 types of sensor. One is accelerometer, inclinometer, and the GPS. As I mentioned, inclinometer gives us displacement, and we have put at 10 floors, I will show you the location, and we have different types of accelerometers, biaxial, triaxial, and uniaxial. And mostly we will measure the horizontal vibration to mutually perpendicular. I'll show you the locations. And it is spread at various components. And how did we choose this? We have done a very detailed finite element analysis, and we have choose the locations where the best location to measure all the characteristics, vibration characteristics of the building. Typically, this is the sensor distribution what we have. We have 3 biaxial sensors at these locations. In the middle, we also have an inclinometer in all the floors. Now, the data architecture is all the sensors are connected by wires, and all the data is going in a data logger. That is, this is at Alhamra. This is the data logger room at Al-Hamra. And at Kisar, we are getting, these are wired and all the data is stored here. And we also have a temporary server at Al-Hamra. From there, by wireless, it comes to our Kisar such a monitoring center, and where all the computations are done. We extract all the model parameters and we track the frequencies, and all the processing is done at Kisar. And so this is the communication architecture. And as I mentioned, one of the very important components was finite element. We have a very detailed finite element model of this structure. So we know everything about the structure, mostly. And very interestingly, we were able to match this with our measurement very accurately. And this is we have modeled all this. Those who are in modeling, we have modeled with all the beams and columns with Euler-Bernoulli beam. You know, if you go to any software, you have n number of beam elements, right? And all the slabs are modeled as a rigid plate. But it also has a shear walls. It also has a shear walls. These are shear walls actually. Those are modeled as shell element. That's not rigid. It's a flexible shell element. These are actually external shear walls. That's an interesting flair. This is actually a concrete wall. These are modeled as shell element. Now this is the eigenvalue analysis, and you can see the modes what we extracted from FEM. This is what we are tracking actually for the continuous monitoring, and of course this mode shape as well. And this is the data what we extracted from. We have actually, as part of this software, as part of this project, we have developed our own in-house software for data processing. We have our in-house software for very advanced signal processing, for example, stochastic subspace identification, frequency domain decomposition. We have our own software for carrying out this analysis. And you see that it is matching exactly. And not only this, we also do extremely, over a long time, we do very rigorous statistical analysis using this model parameter. By the way, when we measure vibration, it will tell you only the acceleration. The remaining information we have to extract. We have to process and extract the model characteristics and other details. So these are the things which, for example, these are not easy. The mode shapes and other things to match from data is, frequencies are generally easy. If you put anywhere, you can actually extract the frequency. But extracting the mode shape, this is actually from our sensor. And this is actually matching exactly with our finite element model as well. One of the things is what we have also developed is a fragility curve for the building. At what earthquake, at what is the maximum earthquake it can survive. So that's very important information. For example, this is very crucial for an SHM. If an earthquake happens, you don't have to do any processing. If you have a fragility curve, you will be able to tell whether it has caused any damage or not if you have a fragility curve. I think this is very important as a government authority. If an earthquake happens, if they have measurement at various regions in Kuwait, and based on the comparison with the fragility curve, we can tell which area has affected more. Accordingly, they can operate their emergency response. This is a very important thing which I said, GPS. See, look at this. This is the movement of this building, Al-Hamra, over during, this is the, if you look at the orange and the blue curve, in each year, in winter and summer, it moves on one side and it goes back on the other side during winter. So this is very interesting thing, that means it is actually a very important parameter, a structure like this. I think this is especially because this is highly asymmetric structure. By the way, Al-Hamra is the first structure in the world, one of the tallest building, which is designed asymmetric. You don't see any tall building which is designed asymmetric. Okay? So GPS we initially thought we actually used only to measure the displacement, but it is so happened that we were able to measure the vibration, we were able to measure the deformation. It actually does the dual purpose. We actually were able to, sometimes if you put inclinometer, if you ask anybody, they will say that put inclinometer. And once you put inclinometer, you will know that, okay, I don't know what to do with this. This inclinometer is so it will throw you some junk data. We actually really struggled with this. And later we were able to match exactly with the inclinometer. Now we know exactly how to estimate. We were able to match with the GPS measurement, how much is the tip is moving. And in fact, in many cases, we don't need an inclinometer. I have put in the inclinometer in the bridge, and I know what data it gave me. So now I know where to put the inclinometer, what type of sensor to choose. This is the data which we got, the vibration, the frequencies, which are what I have shown using the GPS. We were the first one to measure the earthquake, the response of an earthquake using GPS. So this is the vibration data which we measured, how much it has moved. This is actually, when we first started at Alhambra, we did not have much sensor. I used to go there, I will ask Alhambra, the security, I have to wait 1 hour in the down to open. They will think that this guy, why Dr. Jafar is coming all the time? The security will never respond. And they thought that I have sensors all over the building. And I did not have any sensor. I had only, the beginning, we had only one GPS on the top. So unfortunately or fortunately, I don't know, this 2017 earthquake, the building, most of the building here vibrated. I think it was around 6:30. I got a call from Alhambra. You have a lot of sensor. What happened to our building? Our building although vibrated. What do I tell? I don't have any sensor. I have never measured vibration using GPS. I don't know what to do. So the same day, I went there. I downloaded the data from GPS. Fortunately, we were able to track the high frequency data. The vibrations were very clearly tracked, and then I gave them, this much is your vibration, this much is your design value, and this is the before condition, this is the after condition, your building is perfectly safe. Thereafter, they called me, Jafar, do you want to come here? Do you want to do anything? So that is the value, they realized it. And in the next meeting, I remember, not even the chairman, the owner has come and attended, and thereafter, of course, we have very high dense instrumentation at the tower. So the value, I think they realized during this. Now, this is the only building, even after every earthquake, they know how much it has been moved. Do you know that even with the Turkey earthquake, many buildings have, in Kuwait has vibrated due to the Turkey earthquake, that is actually 3,500 kilometers away. In fact, it reached, after the earthquake, it took 4.5 minutes to hit the buildings in the ground surface in Kuwait. The wave traveled 3,400 kilometers. That took around 4 minutes to reach Kuwait. And the vibration was not very small amount. So this is our algorithm, what we have developed. We have a very nice, excellent software which we developed in Kisser. As part of this, I think the time is up. I may have to. This is another very interesting work we did for the bridge. In the bridge, again, we have different types of sensors. What time is it now? I think we can, if it is time, we should stop. Is it time? Maybe we can, I think I will skip this. Here we have implemented one additional capability. We have a strain measurement sensor, but additionally what we have done, not only monitoring the structural safety, we also implemented, in real time, we can measure the weight of the truck. I think that's a very good information. In addition, that's a byproduct, that's a secondary information we can get it if we can implement all through Kuwait. And in fact, some of the data I can show you. See, look at this. I don't know how much, what is the weight of some of the trucks. It's actually really heavy, much heavier than the design load. We have the data, the estimate, and if you look at this, the national days, the vehicle load is extremely low. You know, this is on February 26 and 25. I think with this I will stop. Now currently we are doing some advanced work at Kisa. This is for the Grand Mosque. Grand Mosque is again a different challenge that the structure doesn't, if you put vibration, if you put accelerometer, it's also very difficult to extract certain parameters. We really struggle to understand. It doesn't have a finite element model, but now we are on track. This is a couple of papers we published purely for the machine learning model, how to estimate the damage, the recent papers. Now we are also working something on physics-informed machine learning. This is what I said, just based on Ashur has just completed his master's thesis on this topic. Just based on the video record, just using a camera, we were able to match the vibration of any structure. We were able to extract the model characteristics. We did with our... So with this, I think I will stop for the time being. There are a lot of things. It's time up. So maybe if you have time for some question.
5 minutes for questions. If anybody
How much does Alhambra move at the top?
During the earthquakes?
Not just generally and under wind condition. Does it move at all?
Yeah, it moves around 100 millimeters.
100 millimeters.
Yes, on one side and the other side. So it's around slightly more. I don't want to give the exact value. So yes, it is more than 100 mm on one side. It's actually either rotates. You know, it's like a wind turbine being twisted. We must have heard, twisted beams, right? If you do pull any twisted beam, it actually rotate as well. This is actually, if you have seen the wind turbine blades, it has actually a twisted shape. So similarly, even if it is elongate or compress, it's actually rotate. So if you apply vertical load, you get a horizontal. That's because of the coupling in your stiffness matrix. Your material matrix, you put E as, it will be a diagonal, right? E1, E2, E3. All off diagonal terms are 0. But in this case, you will have non-zero off diagonal term. That's because of the coupling, geometric coupling, not in the material part. It's a composite. Those who are doing composite, they know that, you will have non-diagonal, non-zero off diagonal terms. Anyway.
This data which we are collecting from the sensors.
Yes.
So who is monitoring or who is checking?
We. Ashur, this guy.
So 24 hours?
The calculations are done automatic. And if there is anything beyond the threshold, we get email. But we check every day.
How many emails you have got? Yes.
Pardon?
How many emails you have got so far?
Initially we get a lot because I don't know what is the threshold. Now I know really well. Now I slowly increased. Now very less. So now our confidence is very high.
Because as I'm saying, all the time you are not there. So you take a certain period.
Yes. Our computations are done automatic. Our computation, it's not done in real time. We are not doing real time. We set a particular time. That day it will run. But every day morning we check, has it been completed? Sometimes it crashed, yes.
So there are so many tall buildings
in
the city. Who is deciding that I want to have sensors put in this? Is the client deciding that? Is KISR deciding that? Who takes the decision that I want my building checked?
Interesting. Actually, after this, we have given a recommendation. It should be mandatory. It should be mandatory. After certain height, you have to have a minimum number of sensor and where to put it. But there is no policy for us. So now it is completely under the landlord or the landlord's discretion. Yeah.
Many of them are coming to you to say, please install sensors.
Yes, these days, yes. These days, yes. Correct. I think it is very important. It also has a national value. So I think after certain height, it is important to put at least, it's not dense. The question is how many sensors we put it, right? Isn't it? And in many cases, the owner doesn't want to know the trouble as well, right? So these are, these are the political...
but I think your point about it becoming mandatory after a certain height.
Yes.
It's critical for the country. I mean,
yes.
Taller and taller buildings are coming up.
That's right.
It does make sense to do something like
that. That's correct.
Right.
think there is more basic question about the general loading.
Yes.
We don't even have a standardized loading or design in Kuwait. So that is the more fundamental than the FHM.
True.
Yeah. And one more question I have is related to the fragility curves. When you develop the fragility curves, how you decide about when your model is a nonlinear model then?
Yeah. We have a nonlinear. We have done a complete nonlinear dynamics.
Okay.
Yeah.
Okay, so the nonlinearity, how you model the material and the geometric nonlinearity?
We have concrete nonlinear. Yeah.
Standard.
Yeah. As of now, see, fragility curve, you don't need a very accurate. See, there is no other way to check it, right? How do you check let me ask Dr. Muntaz, how do you check the strength of concrete? Compressive strength.
You mean taking samples and
Break it, right? So we can.
there are some non-destructive tests.
Yeah, but to be accurate, you have to break it, isn't it? So we cannot break the, right? To know the exact strength, you have to break it.
You have to take
So this is the problem with the nonlinear analysis, especially in the real structures. So we have used the standard nonlinear models.
You mentioned that sensors are getting very cheap.
Yes.
Can you just elaborate how cheap? Because I know that structural health monitoring is expensive.
Yes.
So how cheap?
Yes. That's a very good question. Not only for us, actually, the sensors are these days cheap. So you have different types of sensors. The sensors you can get it from $200. Any nice accelerometer. Ashur, he just made in our lab a sensor for 2 kD. And we were able to match in our lab. How much did you buy? He bought it from Haveli. Tell me, I'm not joking. So we have, but can I put that sensor in the Alhambra? No. So there are various, Alhambra we are using a force balance sensor, accelerometer. This costs, again it varies from 1000 kD to around less than 2000 for one sensor.
So a sensor would be about 1,000 to 2,000.
1000 kD, yes, let's say that.
Your fees would be about 10 times that.
No, but we are doing for free. Kisar doing free. Government. See, Dr. Saud is there. How much did you get money? Let me ask him. He was there. He was my neighbor for a long time. So he's asking for all this work. He's saying we will get a lot of money. These companies will pay us.
I have a question.
Yes.
Alhamdulillah.
Yes.
But if we take it realistically, is it a learning project?
Yes.
Like clients? Because if there's a new building, almost like Alhamdulillah,
Yes.
do you need to do all the instrumentation?
No. That's a very good question. I think what you're asking is, can I do at a cheaper cost, right? Yeah.
You take the worst case scenario is on the top.
Yes.
So you can just, if you monitor the top, then let's say seismic,
Yeah.
mostly it's a high buildings and tower.
Yes.
Where you get let's say it's automatic and then you have a warning and you have evacuation immediately.
Yeah.
So you need only one or two, something like that.
Yeah, one we can do, but let me ask this structural engineer.
You're very generous in Alhambra, so you got like a learning.
Yes, that's right. I think you are partially okay. Yes, it was learning. And the second part is also correct. I don't need this many sensors what I have put it in Alhambra. For example, inclinometer, I wouldn't put it everywhere. I know where exactly to put and how many I need. Now, accelerometer, will I go with one? Definitely, I will not go with the one. Because what is your criteria for earthquake design safety? You use something called interstory drift, right? Yes. So one parameter is the maximum displacement. The second one, what they look at is the interstory drift. How much the interstories are. So if you ask these guys, they will tell, I need data from every floor. So I don't need every floor for this. So maybe I know where to put some floors. There is some stiffness change. So to answer, you are overall correct. We don't need this many sensor. We would do much lesser sensor, maybe a much lesser cost.
Can you generalize? Like if you have 10 buildings similar,
Wow. Sorry. Pardon?
can you generalize? If you have like 10 towers,
Yes.
one is insulated,
Yes.
the others are not.
Yes.
It's the same country, the same thing, the same.
This is actually we are working.
Equate all of them if there's.
We are actually working on it now. We have actually a project. We are actually trying to have a transfer learning. I think what Dr. Saud is asking, if I know the performance or movement of this building, can I tell what happens to the right 2-3 building right after? Yes, we are actually doing a work, what is known as a transfer learning, and we are working on it. This is one of the things which we should, yes, that is purely based on data driven.